All right, so welcome everybody at the next International Prague seminar on function spaces. And so it is our pleasure to have here today Rupert Frank from Munich, and he will talk about Sobolev spaces and spectral asymptotics for commutators. And so the floor is yours.
Well, thank you very much. Thanks for the invitation. It's a pleasure to speak here and to present to you some of the things I've been thinking about recently. It's the first time I'm giving this talk, and it's somewhat an experiment because I want to speak about two rather different topics. The first one is really about theory of Sobolev spaces, and the second one comes from spectral theory. And so probably my basic motivation was the second topic, but I hope, at least, so I'm looking forward to your feedback on this, but at least my impression was that the first part and this discussion of Sobolev spaces might also have some interest. And the topic, more precisely the topic, what I want to talk about Sobolev spaces are derivative-free characterizations. Okay, so such characterizations have been around in the literature before. They are very useful. One of its uses, by far not the only one, is in partial differential equations when you want to do regularity theory. And so you don't have derivatives first, and then you want to control some quantities that don't have derivatives, and then they exist, and then you learn something that actually derivative exists. But as I say, I mean, that's one motivation, but there are many others. And so the one particular motivation, or the one particular definition that I will be using uses this oscillation function. Okay, so you have a function f which lives on Rd and is locally integrable, and then for every point A and R in the upper half space, where I just think of A as being a point in Rd and R as a radius, I'm looking at f. So I'm thinking of this point AR as a ball, okay, and then I'm subtracting from the function its average over that ball, and then I'm integrating this object over the ball. And these integrals with the stroke in the middle, they mean that I'm taking averages, okay? And so what I will tell you is that there's a way of characterizing this Sobolev space, first order Sobolev space, in terms of this function. And there are, I mean, such functions of this type have appeared before, obviously, but I think that characterization of this space, not exactly. Anyway, so that's the one topic. Now, the other topic is that I'm looking at commutator operators. Okay, so what is this? So K is a certain given operator. Think of it as a Riesz transform, right? So it's a zeroth order pseudo-differential operator, can be from a more general class. We will actually pick it in a very specific way. But anyway, so the K is a given operator. And then I'm looking at the commutator of K with F. So I'm thinking of F here as a multiplication operator. So what this thing stands for is Kf minus Fk. Okay, and so I'm wondering about the boundedness and the compactness properties of such operators. And it turns out that these properties can be very nicely characterized in terms of the function f. Okay, so and this is where we will see a scale of function spaces appear that guarantee certain boundedness or compactness properties of such operators. And now the theorem, I will tell you a little bit about why I'm putting here some quotation marks, but that's in the background here, goes back to the late 80s and early 90s. And that says that a function belongs to this Sobolev space if and only if this oscillation function belongs to some weak LP space with respect to a certain measure on the upper half space. And that in turn is equivalent to these commutator operators belonging to a certain so-called weak Schatten ideal. Okay, so we have an equivalence of three things. And in this talk, I want to discuss those into a little bit more details. I want to tell you a little bit about proofs and also about sharpening of these results. I mean, these are old results, so we gave alternative proofs, but then also we gave stronger statements which perhaps put these old results in a little bit a clearer light. And then also I want to connect it to some recent things that have been discussed in connection with Sobolev spaces. So that's a rough outline of this talk. Okay, so I will start with topic 1 now, and that will probably be the first half of the talk, and then I'm going to topic 2, and I will compare these two things. All right, so here I can state right away the main theorem. Everything that's up there I have already said, or I assume that this is known. So we're talking about these homogeneous Sobolev spaces, right? Where we just require that the gradient is P summable. Gradient, of course, taken in the sense of distributions. Then we have this oscillation function where we just integrate the absolute value of a function minus its average over a ball. And then we have now, so this gives us a function on the upper half space, right? Where so the points A and R run through the upper half space. And on that upper half space, we define a certain measure. Here it is. So it is just on the RD, it's just dA, that's just ordinary Lebesgue measure. But then in the R variable, which measures the size of the ball, we put a weight on. And in particular, you see that this measure is not integrable for small r. So all the weight, so to speak, of the measure goes to small balls. So small balls really are the thing that matter. Okay, and so now here's the theorem. So we're in any dimension P. I have to exclude the case P equal to 1. I'll talk a little bit about that later on. And then the theorem is that a function belongs to this homogeneous Sobolev space if and only if this oscillation function belongs to the weak LP space with respect to that measure, and moreover, the norms are comparable. Okay, it's an equivalence. Moreover, there's a second part. The second part is that you can, from the distribution function, right, so this is the distribution function of your MF, of your oscillation function, right? This is, I mean, the weak norm, right? That you measure the size of the super level sets. And now if you look at this measure of these super level sets and you go to kappa, go to 0, so you look at as these level sets become bigger and bigger, then in the limit you recover exactly that norm. And well, there's a universal constant there, which you can express in terms of gamma functions if you want to. Okay, so that is this derivative-free characterization of Sobolev spaces. Let me briefly tell you now a bit about the history, why I'm putting these names. So there was some work on everything is really starts with these commutator operators, and Rochberg and Semes worked on this question, and then a couple of years later there was, and they left open a question, and then a a couple of years later, Kohn, Sullivan, and Telemann wrote a paper which has an appendix, which is also written by Sems, and there they prove sort of a version of this equivalence in the case that P is equal to D. It's not exactly that because they don't look exactly at this oscillation function, but it's somehow a close relative of this. They also sketch a proof. They don't have really all the details in there, but I think once one sees it, one can fill in all the details. And so what I did here in this little note was do fill in the details and then add this asymptotic condition, which, as I will explain, is from a certain point natural and somehow, in my opinion, clarifies a little bit what's going on. Anyway, so I think I should tell you now a little bit more about this oscillation function, right? I mean, I'm certainly not the first one to use it, and neither were Kohn et al. So there are many, many classical results where this oscillation function appears. Okay, so I mean, we can think, so for instance, I mean, having a function in a BMO space means exactly that if you take the supremum of this gadget with respect to R, right, then you get a function of A. It's called the sharp function, that this function belongs to L infinity. Similar, there's a result, I think this is Pfefferman and Stein, which says that a function is in LP if and only if the sharp function is in LP. And then you can, I think this was Campanato, you can characterize Hölder spaces in terms of this oscillation function, and Calderon also showed that you can characterize these first order Sobolev spaces in terms of this oscillation function. Okay. Now, in all these classical results, so these are all the classical spaces, you take suprema over R. You don't necessarily have, you can also, instead of taking suprema, you can also integrate. And then you get in the realm of Besov and Triboulet-Sorkin spaces, and those spaces you can characterize in terms of this oscillation function. Okay, I don't expect you to read all these details. I just want to emphasize that the MF function appears here and that they're integrals with respect to A and R. And perhaps one a special case that is somewhat relevant, in particular in this commutator business, is where the order of differentiability S is equal to D divided by P, and where, I mean, P is equal to Q, right? And then you get these fractional Sobolev spaces with differentiability order between 0 and 1. And then you see that then this becomes real LP norm, and what you get here is you get this oscillation function in LP with respect to this measure, the one that we had on the previous slide. But the point that I want to emphasize is that in all these results, what one sees is this oscillation function in some strong LP space. Right? It's not a weak norm of the LP space that one takes. If one goes here, if one would go here in these Besov or Triboulet-Sorkin spaces, if you would go to higher integrability order, then what you would do is you would subtract not only a constant, but also a first order polynomial, say, or even a higher order polynomial, right? But then once you've done that, you again compute a strong LP norm. And the thing that I want to advertise here is that at this critical case, where S is equal to 1, right? The one that's missing here, there you can work with a weak norm. And that might be or could be perhaps have some applications. Okay, now this also connects to something that has become popular in the last 3 years or so. And this is work by Brices, Van Schaftingen, Seger, and Young. And they also wanted to get derivative-free characterizations of Sobolev spaces. So let me go through their result real quick. You see the way I've written it is exactly the way I formulated the previous theorem. So there is a certain, you want to characterize membership to a Sobolev space with an if and only if condition, oops, if and only if, right? A certain function belongs to a weak LP space. And then you want to have a limiting statement that if you look at these super level sets and you take the limits, then you really, I mean, the weak norm or the functional that appears in the definition of this weak whatever quasi-norm gives you back the norm in this space up here. Okay, now what does this mean more precisely? Brices and co. look at a function of two variables. Okay, so it's f of x minus f of y divided by x minus y to a certain power. And the power is tunable, right? I mean, there's a gamma there, and gamma is an arbitrary non-zero parameter. And so they look at this two-variable function, and they look at it as a function on this weak, I mean, in a weak LP space over this RD times RD. And then they have a measure there as well, which is not the measure that we have, but anyway, it's has dx dy, ordinary Lebesgue measure, but then it weights with respect to the distance x minus y, again to a certain power, where this power is chosen to match the power that appears in this function. Okay, and then once again, as I just said, you can characterize homogeneous first order Sobolev space in terms of such a derivative-free quantity, or more precisely, a weak norm of this quantity. And this is sort of an optimal condition, and it's saturated in a limit. And which limit you take here depends on whether you have gamma bigger than 0 or gamma less than 0. That's sort of, remember when I told you before that our measure is not integral at r equal to 0, that meant that we're zooming into small balls. And a little bit in that spirit is that you have to take two different limits. So this theorem here, which appeared last year, is motivated by earlier work by Nguyen, and also who I guess considered the case, let me see, of a positive gamma, or perhaps, yeah. And then also from perhaps 2 years ago, a work by Brices, Van Schaftingen, and Young, where they considered positive gamma. They say, here negative gamma. This is positive gamma. Yeah, and so they proved this theorem, and there has been quite a number of follow-up works where they have explored this further. Some results that I did not write here are also about the case p equal to 1. Right? I have not stated those yet, but they do have some analysis. So the situation there is complicated. And I have already stressed somehow the similarity between this theorem and the theorem I discussed on the previous slide. I also want to point out that there is a difference, namely, they have a purely pointwise criterion, right? You look at this function, it's just f of x minus f of y. This is purely pointwise. Whereas in the criterion in the previous slide, you have these integrations. when you look at the oscillations. So while they look similar, there are also some differences. And then I should mention that these authors, I mean, both the first works and also in this recent book, they were not only interested in this from an academic point of view, but really they had applications in mind. I think this goes in this direction of questions of lifting for maps, Sobolev maps taking values in a manifold. But I refer you to the original papers by Brecis, Boga, Mironescu, and there's a recent book by Brecis and Mironescu. Just wanted to emphasize, I mean, that they had some things in mind. Okay, so let me show you the theorem once again. This was the theorem that we had discussed. I'm just restating it. I have already told you that in the special case, P equal to D, Kohn and co-authors had a close relative of the first part of this theorem, and where you have a dyadic version. So see, I'm looking at all centers and all radii, and roughly speaking, what I guess that actually goes back to Rochberg and Semmes, what they considered were just dyadic cubes. And then you have to formulate the questions a little bit different, right? I mean, this measure is not there really, but it's very similar in spirit. But on the other hand, when you have something discrete, I'm not sure whether you can even expect an equation like it, an equality like this to hold. So there the motivation came certainly from this Brecis et al. Work, where they show that you really get an equality in the limit. I should mention a small extension, namely in this oscillation functions, right? We used an L1 norm. We integrated f minus its average to the power 1. But you can also integrate to the power q, where you have certain restrictions on the q coming from this p that you want to aim at. So that's simple. And then let me make a few remarks about p equal to 1. The basic message there is that it's open and we don't know. And even Rochberg and Semmes 40 years ago, that was before this theorem was proved, they had written a paper about it and explained somehow that this is a rather difficult case. And I think despite the progress that has been made, this is still not understood. So let me tell you a little bit more precisely what the situation is for p equal to 1. So first of all, these asymptotics are fine if you have, say, a nice function, two derivatives and compact support. All right. Now, based on this, you can show that if your oscillation function is in weak L1, then your function is of bounded variation. On the other hand, there's a function of bounded variation, and you don't have to be very creative. You just take the characteristic function of a ball, you do a short computation, and you see that its oscillation function is not in L1 weak. So it's not that functions of bounded variations characterize this condition. We don't know what characterizes this condition, or whether there is such a simple thing. So I think that would be, it's still an interesting question to explore that better. Then, of course, another natural question would be to look at higher order Sobolev spaces. As you might have guessed, or as I indicated earlier, was you would subtract higher order terms, but some are higher order nomials, but in some sense, this is not so natural anymore. I mean, the average was a very uniform quantity, so you might get an equivalence, but whether you get such a nice asymptotic formula, this is not clear to me. And now then, motivated by this work of Brecis and co-authors, there is a a natural conjecture there, right? Namely, see, when you look at the theorem, one direction says that if your MF function is in weak LP, then you have a gradient in the distribution sense, which is an LP. Now the question is, do you really need this supremum to be bounded, or is it enough if the lim-inf of this quantity is finite? Right? If you look at this formula, and if you're very optimistic, then you might say that the lim-inf should be enough. So then if the lim-inf is finite, this already should force this quantity to be finite. So you might get this. So this was proved in actually quite beautiful paper by Bourgain and Nguyen in the setting here on the previous slide. Actually not in the full setting, but in one of these cases where gamma is, I forgot it again, I'm sorry. I might have said it wrong before. So it was in one, for one very specific choice of gamma, it was shown in this short but beautiful paper of Bourgain and Nguyen. And I'm also able to show it here in the case d equal to 1 in the setting of this theorem up here. But in general, it remains open. Okay, so that would somehow complement this and strengthen this result. And open questions of that type were asked by Brices in the previous setting. So there are more open questions of this type if you're interested in this. So let me now spend one short slide about some ideas in the proof. Okay. Yeah, I will be very brief, but just that you see what's going on. It's not particularly deep. The proof splits naturally into two parts. Okay, so the first part is if your gradient is p integrable, then your oscillation function belongs to this weak LP space. And that's almost a one-line proof because you apply Poincaré's inequality, right? Poincaré's inequality says that the oscillation function is bounded by the integral of the gradient. And you see that there's an R in front. Now you bound this by the maximal function, right? There's an R times the maximal function. And now you just compute this measure, right? I mean, the measure of this super level set where instead of MF, you put in your upper bound. And so you do the R integration and then everything comes out nicely. You use maximal inequality at the end and that's it. So it's really a very short argument. The other direction is, I mean, you have to work a little bit harder, but it's also doable. So you look at, assume that your oscillation function is in weak LP, and you want to argue now that your gradient is p integrable and that you have the asymptotic formula. And so how do you do this? Well, you start with nice functions. Okay, and by nice function, I mean that you have two derivatives in L infinity. And then I also want to prove a local version of the statement, meaning I put in now a set omega. Okay, this is a bounded open set. And now I'm looking at this measure where I'm only integrating over centers. Remember the oscillation function is defined on points A and R, and I'm restricting my A's to lie in the set. And then I'm proving this asymptotic formula. So only in a local, even in a local sense. Okay, so even if I intersect the left side with a bounded open set, then I get this. However, the price I pay is that I only do it for smooth functions. And so how does that work? Again, the argument is pretty simple. See, let's look at the oscillation function. So we have a function, we subtract its average. So that function minus its average, that's of course 0 when the function is constant. So in other words, it should be the gradient of the function that matters. And now if you do a little back on the envelope computation, you see that this oscillation function actually behaves like the gradient. We're talking about small r, small balls, right? It behaves like the gradient at the center times the radius, times some universal constant. Okay, and I want to emphasize that you should compare this equality, this an asymptotic equality as r goes to 0, with the bound we had up there, right? There it was r times the maximal function of the gradient. So they are very closely related. I got rid of the maximal function, so to speak, in the limit. And then you do the usual things, you mollify a little bit, and you use these local asymptotics. And at the end, you deduce that f actually has a gradient in LP. And then once you know this, you go back that you know something about functions in LP, and then you extend this part A to the full case. Anyway, that's all I wanted to tell you. Perhaps the takeaway message is that small balls matter because this is where the measure is singular, and there you do a computation. Anyway, so that's the first part of this talk. And now I want to go to this commutator business, which, as I said, was really my motivation to looking into this. And there, an object that has appeared recently quite a lot, in particular in context maybe with non-commutative geometry, is a so-called quantum derivative. Don't worry about these words. I don't think they have some particular deep meaning. What the object we really care about is this here. Okay, so you have a function f, a scalar function on Rd. And now you look at the commutator operator of this f with a certain operator, which is, you can think of it as a Riesz transform. Okay, so it is singular integral operator, and for simplicity, let's assume it's translation and dilation invariant. And the fact that in non-commutative geometry, one builds this operator in terms of essentially a Dirac operator, this doesn't really matter. So, I mean, if you haven't seen this, don't waste time on reading this or worrying about it. It really, everything holds for a general choice of R. But I mean, this is the choice that people do make. So now, if we go back to probably the 70s, there is a famous result of Kaufmann, Rochberg, and Weiss, and then later by Uchiyama, which says that this operator, they were not looking at these quantum derivatives, but I mean, they were looking at these operators. Anyway, it's the same thing. So they say that this operator is bounded if and only if your function f is in BMO. Okay, so that's already, I mean, that's sort of remarkable. Why? Because, of course, the object itself, so R times F, remember F is a multiplication operator, and R is this operator, which is obviously bounded on L2. So R times F is not necessarily a bounded operator, and F times R is not necessarily a bounded operator either. But if you take the difference, right? Taking a commutator means you take a difference. It's Rf minus Fr. When you take the difference, then it becomes bounded, even though the f might be unbounded. And so the unbounded f's that are allowed, these are exactly these BMO functions. And then if you're a tiny little bit better than BMO, then your operator is compact. And a tiny little bit better means that you're in the closure of continuous compactly supported functions of BMO. Okay, so this settles completely the boundedness and compactness of these operators. So now one goes on in spectral theory, one introduces so-called singular values. Okay, these are the, of a certain operator K, these are the square roots of the eigenvalues of K star K. And compactness means that these singular values go to 0. And now we think of measuring the degree of compactness by quantifying how fast these numbers go to zero. And so the question now is, can we characterize this degree of compactness of these operators in terms of properties of the symbol? And the answer is yes. Again, a famous result of Janssen and Wolf from the early 80s says that this operator belongs to the Schatten space P. In other words, the singular values are P summable if and only if the function f belongs to this fractional Sobolev space. Okay. Now, of course, somehow these Schatten spaces are nested, right? Because the little LP spaces are nested. So somehow the better your function gets, so you start with a BMO function, and then you get better and better and better, meaning that these spaces, your differentiability index increases. And as I said, these spaces are nested, then these operators become more and more compact. And that goes on all the way until P reaches D. That's where this summability index, the differentiability index, sorry, the differentiability index reaches 1. And at this point, you don't get any more better. Okay, at this point, you are in Schatten space with exponent D, if and only you have the constant function. In that case, of course, the operator is just 0. Okay, so as the smoothness or the regularity of this symbol f increases, you get better, the compactness of the operator gets better, and at some point it stops. And so you ask yourself, what happens at the end point? And this is now what this theorem by Kohn, Salve, and Telemann is about, and this improvement that I want to tell you about. Let me just, before I do this, let me check. So I've copied these, the first few lines on this slide, they're just copied from the previous page. But what I've done is I've written the things out in terms of my oscillation function. Okay, remember, BMO means that the oscillation function is bounded. This fractional Sobolev space is characterized by having, that's what we've seen on this slide about Besov and Triboulet-Sorkin spaces, having this oscillation function in LP. Actually, you could characterize this space as well in terms of the oscillation function. I just didn't write it down because it takes a little bit more. And then finally, it's a little exercise to see that actually this oscillation function can only belong to LD if the function f is constant. Anyway, so you see this, that you measure the properties of f as in terms of this index of the integrability index of this MF function. And so here's now the endpoint result. Okay, so your operator belongs to the weak Schatten ideal with exponent D. So that's defined by having the singular values in the little LD weak. If and only if your function f belongs to the homogeneous Sobolev exponent with integrability index D, when dimension D, by the way, and D is greater or equal than 2. And you have an equality of norms. I mean, not equality of norms, but equivalence of norms. Okay, between the functional that defines this weak Schatten space and, well, the norm that we have on the other side of the if and only if condition. And then there's the second part, and the second part tells you that you even have an asymptotic equality. So just like we know it, as we've seen before, right? This is this weak functional. I mean, the functional that defines the weak norm. If you look at a limiting regime, take n to infinity. So you go to the singular values, which are very, very small, look at their asymptotics, then you recover exactly this term that appears in the if and only if condition. And there's a certain constant that you can write out. And so what you see here in particular is, if you combine this with the previous theorem, you see that you are in this weak Schatten D space if and only if MF is in the weak LD space. Okay, and so you might, when you looked before at the result, it was a little bit strange because you had these fractional Sobolev spaces, and there when this differentiability index jumped or went to S equal to 1, the conditions somehow jumped. You went from a strong LP space to a weak LP space. But when you look at it from the point of view of these Schatten ideals, then you see, well, yes, here also for the Schatten ideals, we went from the SP spaces to the weak space. So there it's the same jump that we see in this oscillation function. All right, so that I hope explains what this result is about. I should, concerning references, I was, I put this in the same, with two groups of authors here because to emphasize the similarity to the previous theorem, what I really mean is Kohn et al. Proved the first part, so this equivalence. And again, the word proved here means that they sketched the proof. And then there was a recent work a couple of years ago by Lord MacDonald, Kochev, Zanin, who proved the first part under an additional L infinity assumption. They gave, full details, and it's completely a quite different proof. And so what we did this year was we removed this L infinity assumption that they had, which sort of does not really figure in the asymptotics. And most importantly, we provided it with this really asymptotic equality. Okay. And so here, once again, I show you the theorems next to each other so that you see the similarities. So, this is the theorem we had before, this derivative-free characterization of Sobolev spaces. I've just put D equal to P in the previous notation. And, well, we have the if and only if condition here. And then we have the asymptotics. And here, this is the theorem about the commutator operators. Again, we have the if and only if condition, and we have the asymptotics. And to make it more suggestive, see, what I've done is I've written this quantity here. The quantity involving the singular values in terms of, accounting problem. So instead of saying that, look at the nth singular value, raise it to the power d, multiply by n, and take n to infinity, you could as well count how many singular values do I have above kappa, then multiply by kappa to the d, and then let kappa go to 0. It's an equality. This is elementary. Okay, but now when you write it in this way, you really see how similar this thing here is to that thing up there, right? And so that somehow very, very morally suggests that the number of singular values bigger than kappa is roughly the same as the measure of where this oscillation function is greater than kappa. And that's sort of really the basic idea behind the Rochberg-Semmers proof. The equality sign here is a little bit more complicated. You have averaging going on, you have maximal operators going on, but somehow in an ideal world, this is the equality you would have, and that's what guides your intuition. And this is sort of also the intuition that helps you translate between these things. And so to tell you again a word about this Kohn, Sullivan, Telemann, Sem's proof, they used this result of Rosberg and Sem's, which compares singular values to oscillations. Remember, they had this dyadic measure of oscillations, which is just as fine. And then, therefore, in this theorem, they replaced this quantity, roughly speaking, by that quantity. And then they proved this thing, this equivalence for the Sobolev spaces to deduce this result down here. Okay, so that's why they were interested in this theorem about Sobolev spaces. And so our alternative proof is independent of the Sobolev spaces. Okay, so while these Sobolev spaces are kind of in the background, we really don't use them. And what we do instead is so-called double operator integrals. This is a tool from operator theory, which is quite powerful when you have to deal with commutators. And there have been quite a number of significant advances in the, whatever this, 30 years between these papers. So we could all use all these tools. I mean, the proof of Rosberg-Sem's, this is a beautiful paper, and this is very powerful machinery, and it's great to have this. Our goal was just to have a perhaps more streamlined and more direct proof that really makes use of the more concrete quantities that we have at hand. But it's really meant as an alternative. And then even more importantly, we wanted to get these asymptotics. And that's where sort of this more general approach probably cannot give you anything. And so that's what we managed to do. I should perhaps say for the experts in the audience, we're talking about something like semi-classical asymptotics. It's related to something called Weil's law. And somehow why this is somewhat subtle is, of course, it's a commutator. And so the term that you would naively believe is the leading term that is just zero because of the cancellation. And so you have to capture this sub-leading term. And it's remarkable that you can do this really under minimal assumptions. I mean, that's really the why, from a spectral theoretic perspective, this result is quite amazing, because, I mean, you can really prove the asymptotics under the sole assumption that the term that enters the asymptotics is finite. Right? I mean, if this term is infinite, then there is no way to get asymptotics. But as soon as it is finite, you do have it. And so there are very, very few families of operators where you have such an if and only if statement, where you have really asymptotics if and only if the asymptotic can be written down. And of course, the pioneers of these spectral asymptotics under weak regularity conditions are Biermann and Solomiak, and Rosenblum made also some substantial progress, had substantial results there, mostly related to Schrödinger operators, but not only. And yeah, as I said already, so we do not use, I mean, Kohn and company, they used this Sobolev space theorem, or their replacement of the Sobolev space theorem. We do not use it. But nevertheless, I mean, having that theorem and seeing it next to each other kind of inspired the techniques that we're using. Let me tell you now a little bit. I mean, so we've seen this analogy in proofs. Remember, there was this question there at the very end, at the very beginning that I told you, where I said in the Sobolev space theorem, is it enough that the lim inf is finite to already be able to deduce that the gradient is p-summable, right? That was this conjecture down here. I emphasized that Brices and Co have made similar conjectures in their context. Okay, and that I can prove it in dimension 1. Anyway, so this was the conjecture about Sobolev spaces. Now I want to go back to these commutator operators. And of course, there the natural analog of the condition would be if the lim_inf of the singular values. Now I've taken the dth root of this, so I've written n to the 1 over d Sn. Right? If this lim_inf is finite, does this already imply that f is in the homogeneous Sobolev space W1? So it's a natural conjecture in terms of what we said before. There's a tiny little result towards the evidence, namely in particular. So this is why this is actually the reason why Brice's has put so much emphasis on this conjecture. He wants to find conditions when functions are constant. Okay, because this is important in applications. All right, and so in particular, you want to say that if this lim_inf is equal to 0, then if the conjecture would be true, right? If this lim_inf would be 0, then it's finite. So the function is in W dot 1D. So therefore, we can apply the theorem, and from the asymptotics, we get that then f is constant. Now, a small step towards this is this theorem here. Okay, so now I'm assuming that the lim_inf is equal to 0, and I'm deducing that the function is constant. It's not quite as strong because I have to do a little bit of averaging. Okay, so I have to take the numbers, add them up to n, and then I have to divide by n. Okay, so there's a little bit of averaging going on, but otherwise it somehow goes in the spirit of this conjecture, and in particular, I mean, in the main point of this conjecture, get conditions for the function to be constant. Okay, so I think actually my time is up, or should be up, so I want to very briefly summarize what I've told you. I spoke about two different topics. The first one was a characterization of the Sobolev space without derivatives based on the oscillation function, more precisely on a weak norm of this oscillation function. And so this might be, I hope, give some ideas for further study from the point of view of function spaces or interpolation theory. Yes, and the second topic was where we looked at these commutator operators, and we saw that the quantity of the symbol f is in one-to-one correspondence with the compactness properties of these operators. Okay, and I've shown you that one can prove sharp spectral asymptotics under really minimal regularity assumptions on f. And why the point that I put these two things together in one talk is that there is really a similarity both on the level of results, on the level of proofs, and also sort of on the conjectures or the generalizations in which one would like to go. Anyway, that's all I wanted to tell you. Thank you very much for your attention. Thank you.
So thank you very much, Rupert, for this very interesting talk.
Thank you.